All right, good morning, and thanks to the organizers for allowing me to give this talk today. I'm just going to jump right into it. Tom briefly mentioned this. This is, recombinative desorption. This is the heart of the model that I'm going to present to you. Very simply, if you supply heat to this, you will form water through reaction of these surface hydroxyls. I just want to really briefly talk about this. This is called a temperature program desorption curve, and it's described well by this Polanyi-Wigner equation. And the key part here is this part right here. So this is recombinative desorption. And I just want to show you the effect that the metal ions have on that. So quartz, silicon dioxide is what usually people are familiar with. Heating that up to drive water off requires significant temperature, about 500 Kelvin or so. Here you can see that we're down to about 250 lower than that. And these temperatures are accessible to something that's happening on the day-side lunar surface now. So the chemistry of your mineral surface does have a huge role in that. Here is a snapshot of the melt rate that our collaborators at NASA Goddard, particularly Juan Diego, did. He basically updated this Intella model, which many people are probably familiar with. By taking into account all the Jupiter family comments, all the Oort family comments, et cetera, and calculating this melt rate. All right. So, and here's just at a full moon, you can kind of see that all of the melt is centered around the equatorial region and slightly offset as well. The melt rates on average is incredibly low, though. We're talking about femtoseconds femtograms per centimeter squared per second, right? However, the key takeaway here is that you're melting the regolith. You're obviously at high enough temperatures to produce water from the recombinative desorption mechanism. This has been done in the lab actually a few times. Schultz a few years ago basically had a BB gun where the pellet was a mineral that was impacting onto another mineral and showed the formation of molecular water that was trapped in the mineral. Shu at the University of Hawaii irradiated an olivine sample with D2 ions and then heated it up with an IR laser and showed the sublimation of water, which is here in blue and red, hydrogen in blue. And then there's been some molecular dynamics simulations as well that has shown that the number of water molecules you're producing is directly correlated with the amount of energy you're inputting into the system. So another question is where do these hydroxyls come from? We're of the opinion that a lot of it is through solar wind hydroxylation. This is an idea that was first postulated by Zeller back in 1966. That's a pretty famous paper in the community as well. These are just some recent examples of these processes. On the left is proton irradiation into an olivine sample done by Micah Scheibel, and on the right is proton implantation into an actual Apollo sample by Jason McLean at NASA Goddard. So you can clearly see that there's an increase in that hydroxyl band, right? Like Tom said, this is a stable thing, right? So the key takeaway here is that if it's IR active, it is a dipole. It has to have a dipole moment, and which implies a chemical bond, and not some sort of metastable hydrogen that's sort of bouncing around internally. This is the crux of the kinetic model that we put together. So here you just have the lattice network, typical lattice network of some metal oxides. You have proton implantation, which creates this hydroxyl defect. That hydroxyl defect will then diffuse to the surface, creating these surface dangling OH bonds, and it also can diffuse into the bulk as well. In addition to hydrogen and solar wind, you also have oxygen ions, albeit relatively much smaller than the hydrogen, but that create these peroxide defects as well. And again, that can diffuse to the surface and down into the bulk. Eventually, you end up with these surface hydroxyls. You supply heat in the form of day-side, typical lunar temperatures, or through that impact event, and you'll make water, and then this process just kind of repeats indefinitely over and over again. From this, we build your differential equations, ask the computer to solve those differential equations, and then calculate how much water is being made. So here's just an example of what's happening as a function of time. So on the top here is the recombinative desorption rates, and on the bottom is the rate of water formation through impact melts. You can see here that as you would expect, the recombinant disruption water producing events is really centered in the hot part of the lunar surface. And it's increasing towards the cold pores as that hydroxyl concentration is built up, right? So it takes longer because the flux is lower in those regions, and then you're eventually going to start producing water through that as well. And so that's why it kind of increases. Interestingly, it has a pretty strong effect on the impact melt because you're removing those hydroxyls faster than the impact melt is. And so the peak water production initially in the impact melt is centered around the equatorial region. But as the recombinant absorption is removing those hydroxyls in the equatorial region, it's then dominated in the colder polar latitudes through the impact melts. So this is just an example of the internal hydroxyl concentration after about 1,000 years. So on the left is what I would call a kind of a low energy case. So the energy that I'm showing here is the energy of diffusion, the activated diffusion for the hydroxyl. So we have low energy on the left, high energy on the right. And so as you would expect, with a higher activation energy, the rate of those hydroxyls going to the surface is much slower. So you're holding on to that water much more longer, right? And this little blip right here is what Tom talked about, right? If as it goes through the full moon and it's behind the Earth, the solar winds should shut off, right? And so the fact is that we kind of don't see that, which would imply that there's some sort of non-thermal process here. This is in agreement with the paper that was done by O.J. Tucker and Bill Farrell as well, that sort of did a similar model where they show that there's this kind of artifact from going into the moon shadow. The other point here is that the low energy is matching more of what we see in observations, which I'll talk about here. So this is a comparison with the MQ data that was reduced by Schwei back in 2017. I just want to point out that the general trend matches quite well, right? There is a couple of discrepancies here. For one, if you notice the scale, I kind of had to change. I'm predicting even in the equatorial regions that there should be about 70 parts per million, which matches more closely with the Apollo missions and even the more recent Chang data sets that have been coming back from that. And then there's also not this huge diurnal shift right here, which would most likely imply either there's a lot of molecular water bouncing around or there's a huge artifact from the chemical composition of the regolith in these areas. And so we can predict, how much water is being produced given certain energies. Now the question is, where does this water go, right? Okay, thanks. And so I built this Monte Carlo model that took into consideration all the lost terms, so photodissociation, dissociated adsorption, genes escape, et cetera. And this is what we see after about 1,000 years as well. So this is a zoomed in region so that we don't see the permanently shadowed regions, which are these bright spots up here. You can clearly see that there is a diurnal change of about 50 parts per million. And this happens, this comes to a kind of a steady state system relatively quickly. After about 100 years, you'll see this on the lunar surface. This is the amount of water, and I want to stress that could be potentially delivered to these PSRs, right? I mean, and this is assuming that PSRs are all uniform of one temperature, which of course is not true. And so there's potentially up to 1 weight percent that could be delivered. However, there is a caveat here. Again, this is assuming that the PSRs are completely static, which they aren't, right? We have fresh regolith that's being deposited through impact gardening, which is going to significantly dilute the sort of mass fraction in the PSRs. Particularly that's being delivered through this impact event and just standard recombinant desorption. Here's a brief comparison with observations that was done by Honeyball as well. You can clearly see that the overall trend matches very well. So we have this nice latitude dependence on the warm dayside temperatures, and it begins to flatten out quite nicely and matches the trend as well when we go into colder nightside temperatures. One thing though is that I want to point out is that the scale is slightly different. So, and which is generally true for all of the observations. It matches the trends. My model predicts a lower abundance. And I kind of think that these observations, in my opinion, are over predicting the amount of water, because there's, 150 parts per million is about a monolayer of water, right? Which should not be stable at these temperatures. And so it kind of makes more sense to that they're either over predicting or that there's some very, very high binding sites on the regolith, which is also quite possible. That's not captured in my model. I guess with that, I'll end and I'll just thank you for your attention.